Thank you very much for the introduction. I'd like to thank organizers for the invitation. And I'd like to talk about associative varieties and for the 2D correspondence. Let me first recall what is a vertex operator algebra. So this is the same as a 2D chiral algebra. Which gives algebraic framework for 2D chiral conformal fields theory. And it's a vector space equipped with a linear map. So I write the field corresponding to A by AG or AG. And so it's not important, but I use slightly different notations and physicists. So this has to satisfy certain properties such as state field correspondence. So we recover element of V taking doing this taking this limit. So in this so we can identify as a vector space V as the image of this map. And the most important property is the locality. This one, which is equivalent to the OPE. So A and B, AG and B. T has an operator product expansion, and this must be a finite sum. And so associative variety of vertex operator algebra is a certain invariant of vertex operator algebra, which is another of the associative variety of the primitive ideas of enveloping algebra of Lie algebra. And so there is a contravariant functor from the category of vertex operator algebra to the category of affine Poisson varieties. So the functor is just given by taking a certain spectrum on some Poisson algebra that is called the Zuse-Shitsu algebra. And this is a finitely generated Poisson algebra. So the resulting variety is a finite dimension variety. And this associative variety is defined. This Shitsu algebra is defined as follows. So we can identify a vertex operator algebra with its image by the state field correspondence. So you can think V as a span of the fields of like this. So AI and AR, so these are generating fields. So you take descendants and consider normally ordered product. And for Shitsu algebra, we consider the quotient of V by the subspace spanned by the elements of this form with which contains at least one derivative. So by considering this kind of quotient, we forget all the descendants. And this quotient space has a structure of a Poisson algebra, and multiplication is just given by a normally ordered product, it's just a product. And Poisson bracket is given by the just first term of the OPE. And it's easy to check that this gives you a Poisson algebra. So you can just spec and you obtain a Poisson variety. And let me explain in some examples how associative varieties look like. So our favorite example is a vertex operator algebra coming from Katsumudi algebra. So let G hat be the affine Katsumudi algebra associated with a simple real algebra G. And then, Thomas already introduced yesterday, if we consider this kind of induced representation, this you get a vertex algebra called universal affine vertex algebra associated with G at level K. I remark that this is not simple in general. So we haven't mod out the null vectors. And the module over this vertex algebra is the same as a smooth G hat module of level K. And because this vertex algebra is generated by the element corresponding to G, you find that the associated variety is exactly the dual of G. The Poisson algebra, the algebra in this case, just a symmetric algebra of G, which can be identified with a polynomial R function on G star. And so if you take so this is a case of a universal affine vertex algebra, but of course you can take the simple quotient, which I denote by LKG as yesterday, and then there are some relation coming from null vectors. So the variety becomes a subvariety of this G star, which is invariant under the natural action of a group corresponding to G. And this is also invariant under natural G star action. In general, it's difficult to compute. But there are some cases where when you can describe such varieties. The first case is our favorite case when LKG is integrable. So this is one of the nicest vertex operator algebra. And then you find that the associated variety is just a point. And in fact, the converse is true. So this affine vertex algebra is integrable if and only if its associated variety is a point. And in general, vertex operator algebra is called Lee's Wasitsu cofinite. This terminology already appeared yesterday. And if this associated variety has dimension 0. And Lee's vertex operator algebra known to have very nice properties. So of course, this integrable affine vertex algebra is very nice, corresponding to West's minority model. And in general, Lee's VUE has only finite many simple modules, and you have a modularity of characters. And you know that the category of module as a natural fusion product. But there are cases outside Lee's case when vertex operator algebra is quite nice. So one of the cases when this representation is so-called Katsuwa-Kimoto admissible. And this is a case when characters of this representation are modular invariant. Of course, integral representation, the character of integral representation are modular invariant, but there are much more cases than the integral representation when characters are modular invariant, and this cases has a level, a fraction levels. And if this is the case, you can show that the corresponding associated variety is a closure of some nilpotent orbit in G star, and you can describe this orbit explicitly. And one of the nice reason that I consider such a variety is that it has a nice, it has a nice compatibility with Drinfeld-Sokurov reduction. So if is a nilpotent element, you can define corresponding the double algebra by taking a Drinfeld-Sokurov reduction. So this is a Drinfeld-Sokurov reduction. Of the universally affine vertex algebra, and depends on the your choice of nilpotent element, or your choice of SL2 embedding. And it's known that the associated variety of the double algebra is the so-called slowly slice at F. It's a transversal slice to G orbits. And more generally, if you have a vertex operator algebra equipped with a vertex operator, a vertex algebra homomorphism from VKG to V, then this VOA has action of affine Lie algebra. So you can take Drinfeld-Sokurov reduction, and you get certain VOA. So we'd like to think this homomorphism as a chiral momentum because it induces morphism from associative varieties, between associative varieties, and because associative variety of affine vertex algebra is G star, so you have a morphism like this, and this is indeed a momentum map for the G action. So this kind of homomorphism can be regarded as affinization or chiralization of momentum. And a fact is that in this situation, associative variety of Drinfeld-Sokurov reduction of V is just a fiber, a product of the associative variety of V itself with a slowly slice, where the fiber product is taken corresponding to the momentum. And so in particular, if you take a Drinfeld-Sokurov reduction of the simple affine vertex algebra, you get just an intersection with associative variety of for the simple affine vertex algebra with the slowly slice, and which is so if K is admissible, this is a some nilpotent oblique closure. So you get the intersection of the nilpotent oblique closure with a slowly slice. And so this kind of thing is called nilpotent through the slice. And so this compatibility is quite useful in the study of representations of double algebras. So application to the representation theory of double algebra was my original motivation to study such varieties. But it turned out it's also useful in the so-called for the 2D correspondence. So let me go on to the 4D 2D correspondence by that is found by Bean, Demos, Liendo, Pilas, Rusty, and Van Ries. So they constructed a map from a 4-dimensional n equals to 2 superconformal field theories to the category of 2D chiral sheet conformal field theories, which can be identified with the category of vertex operator algebras. In such a way that we can compute the Schur index of the 4D theory as the character of the corresponding vertex operator algebra. This is very nice because the Schur index is a very important invariant, and we can use representation theory of VOA to compute a Schur index. And so this functor or map is obtained by considering certain dimensional reduction. So you may think this loses many information of 4D theory. But it turned out this map is I understand that this map is injective in examples so far. So this is very nice invariant. And also it's not surjective because the image is never unitary. The reason is that we have this simple relation between central charge of 2D theory and 4D theory. So if you start with unitary theory, you end up with a negative central charge. So this cannot be unitary. So this means, in particular, this map is not a surjective. So the first statement that this V might be a complete invariant. So this VOA, if you know image of V, you know lots of information about 4D theory. And for people who work on vertex operator algebra, so this is very exciting as well, because 4D theory is extremely rich theory, and we have some interesting family of vertex operator algebra which comes from 4D theory. Now, what is remarkable for me is this conjecture of Beam and Rastelli, which says the Higgs branch can be recovered from corresponding VOA as associated variety. This is remarkable because this is vertex operator algebra is purely algebraic object, and Higgs branch is a very interesting geometric invariant. And so in general, Higgs branch is a hyperkular cone, but by definition, the associated variety of a vertex operator algebra is only a Poisson variety in general. So the vertex operator algebra coming from 4D theory has a property that the corresponding associated variety should be a hyperkular cone. So in particular, symplectic. So this is a very strong condition. And also because everything comes from physics should be nice. But the image VOA obtained as image of a 4D is not Lee's. I explained Lee's VOA is very nice, but this cannot be Lee's in general because this means that Higgs branch is a point. So it's natural to look for some try to relax this Lee's condition for the associated variety to obtain some nice property of a vertex operator algebra, which somehow describe VOAs coming from a 4D theory. And for this reason, we gave the following definition. Vertex operator algebra is called quasi-Lee's if associated variety has finitely many symplectic leaves. So this is certainly some finiteness condition. And the Higgs branch is expected to be quasi-Lee's. And here are some examples of quasi-Lee's vertex operator algebra. This simple affine vertex algebra is quasi-Lie if and only if associated variety is contained in the nilpotent cone. So the symplectic leaf in this style is just a co-adjoint orbit. And because nilpotent cone has only finitely many co-adjoint orbits, so if a variety is contained in nilpotent cone, it's only finitely many symplectic leaves, and you can also show the converse. So this means admissible affine vertex algebra is quasi-Lie. But the converse is not true. And if you take a so-called Deligne exceptional series, which is a series like this, A1, E2, D2, D4, E4, E6, E7, E8, and consider this special level, you find that the associated variety is a minimal nilpotent orbit closure. So the corresponding affine vertex algebra is quasi-Lie. But for D4, E6, E7, and E8, this level is minus integer. So it cannot be admissible. So this is some example outside the admissible representation. And so with Amuro, we studied this VOA from a different motivation. It turned out this VOA exactly the VOA appeared in the papers examples of vertex operator algebra coming from 4D theory. Although we have to remove this G2 and F4. Now, what we can say about the quasi-Lie vertex operator algebra. So we can say the following. For quasi-Lie VOA in general, we can say that there is only finite many simple ordinary representation. So ordinary representation means that the character, the trace, so this is well defined. And for ordinary representation, this character converts to a holomorphic function on half plane. And moreover, this trace function is satisfies a modular linear differential equation. The point here is that the solution space of a modular linear differential equation is by definition invariant under the natural action of SL2G. So together with the beam-Rastri conjecture, if you believe the conjecture and the expectation that the X branch has finite many symplectic leaves, this implies the modularity of Schur index of any 4D theory. Okay, so let me explain more examples of quasi-Lie double algebras. So the WKGB is a simple quotient of this universal double algebra. Then at least conjecturally, it can be described as an image of simple quotient, simple affine vertex algebra by Dirichlet-Sokolov reduction. So this means we can describe corresponding associative varieties. So if K is admissible, then we get this intersection of the Sroddy slice with nilpotent oblique closure, which is called a nilpotent Sroddy slice. And so this is quite well known if G is ADE. And if it's a subregular, because it has this intersection has a simple singularity of the same type as G, but you can take any nilpotent oblique closure, and you can take any Sroddy slice. So because symplectic leaves here is just an intersection of a quadjoint orbit with a Sroddy slice. So this means is that the WKGF is quasi-Lie for admissible labels. So we have a quite large family of quasi-Lie double algebra. And it's known that these double algebra appear as image for this theory or some Aguilar's double theory if K is so-called a boundary admissible label. So boundary admissible label means that the admissible label is a fractional label. So it can be a shifted label, can be written as so this is a rational number. So boundary admissible means this is smallest as possible. So this must be a check for simply list case. And maybe I skip what I wanted to say here. So there's some implication of this Aguilar-Douglas theory, but let me skip. And I want try to talk about the class S theory. So the class S theory is like because X stands for so S stands for 6, and class S theory is obtained from the 6-dimensional theory by compactifying on a punctured Riemann surface, as you know very well. So it has a parameter as a punctured Riemann surface and also a Flavor symmetry group, which is a complex semi-simple group. And Moore and Tachikawa gave a mathematical description of the Higgs branch of this 4D theory in terms of TD, 2D TQFT, and up to a conjecture. Now, this conjecture was approved recently by Braverman, Finkelberg, and Nakajima. So you have a nice mathematical description of Higgs branches. And so one of the statement of Moore Tachikawa is that we can, it's sufficient to describe a Higgs branch for genus 0 Riemann surface, because we can glue the genus 0 Higgs branch to obtain Higgs branches for arbitrary genus. So let me explain the Higgs branch for the genus 0 case. So Braverman and Finkelberg and Nakajima constructed the Higgs branches for the R punctured P1, which I write as MTR, as follows. So this is a finite dimensional variety. But to define a finite dimensional variety, you consider infinite dimensional manifold called affine Grassmannian, where G check is a Lagrange dual. And you consider sheaf on the affine Grassmannian, which I denote by AR, which correspond to the regular representation of G check via the geometric Satake. And you consider box tensor product on this product of affine Grassmannian, and you consider a shrink product. And they show that this sheaf on affine Grassmannian is a ring object, so that the corresponding cohomology, equivalent cohomology, has a structure of commutative algebra. So this is a commutative algebra, so you can take spectrum. So you get some algebraic variety, and so the statement is that this MTR is a possibly a singular symplectic variety equipped with a Hamiltonian action of R copy of G check, where so this R is same as R. So this is already a non-trivial statement. And now there are some initial conditions. So MT2 should have two commuting action of G, and so the MT2 is the most simplest manifold which has two commuting action of G, which is cotangent 1 to G, and MT1 is G cross the constant slow slice. The slow slice for the principal important topic. And the most important property is this associativity property. So MTR plus S minus 2 can be obtained by the symplectic reduction. The statement is that the symplectic reduction is well defined, and we get the MTR plus S minus 2. So this is a very fancy way to define finite dimensional. So Moore Tachikawa conjecture was the existence of the symplectic variety satisfying this condition 1, 2, 3. So this means that the MT3 is exactly a Higgs branch of for the genus 0 classes. And
sorry to interrupt. This is the 5-minute notification.
Okay. For type A, so maybe I skip Coulomb. So now we want to describe the corresponding chiral algebra, which is called the chiral algebra of classes. And these people conjecture that the chiral algebra of classes coming from class S should be also described similarly in terms of 2D TQFT. So we should be able to upgrade everything to the chiral algebra setting. So this means we can want to replace G to the corresponding affine Katsumori algebra. And I want to replace symplectic variety with a vertex operator algebra whose associated variety is symplectic variety X. And that we replace momentum map with corresponding chiral momentum map. And also we replace symplectic reduction with the relative semi-infinite cohomology, which appeared as a coset construction we study. And this is the right thing to do because we recover the symplectic reduction by taking associated varieties. And there's one constraint that to make sense of this relative semi-infinite cohomology, you have to the level of V1 tensor V2 must be 2 times minus HX. So each level has to be critical. So you have to work on the critical level. And so MT2 is replaced by CDO on G, which has a symplectic associated variety isomorphic to cotangent to the G. And MT1 is replaced by a Drinfeld-Sokolov reduction of the CDO. And the statement is that there exists a unique family of vertex operator algebra satisfying similar properties. So this corresponds to the fact that the more attached variety is symplectic, equipped with the Hamiltonian action with GR. And so VT is the CDO and V1 is and we have also associativity for the VGA. And this VOA satisfies the following property that each one is simple and the central charge is expressed as this and have the explicit character formula. And more importantly, we recover the more attached variety by taking associated variety. And this property, A and B, these are properties that this chiral algebra of classes should satisfy. So by the uniqueness statement here, this means that we are here must be the chiral algebra of classes. And the last statement that the associated variety of Wheeler is more attached variety means that the Beam-Rastery conjecture is true for the classes. So this confirms the Beam-Rastery conjecture for classes theory. And we can, in principle, compute the chiral algebra of classes, because although it's a heavy computation. And for SL2, MT3 is, so I just show you the result. The MT3 is just C2 tensor 3. But MT4 is a singular variety, which is a minimal nilpotent closure. And corresponding VOA is a simple affine vertex operator algebra. And the fact that this is associated varieties are isomorphic terminal nilpotent closure reproves the statement I stated before. And so associativity equation implies this following non-trivial isomorphism between VOAs, and we have nice character formula, which is quite surprising because this is not this character is expressed by non-trivial casuistic polynomial. And therefore, for A33, we can also describe that in general, neither of this has a simple description. It's it time to stop?
Yeah, we have one.
Yeah, yes, yes. Sorry.
Sorry, are you stopping here? Sorry, are you stopping here?
Sorry?
Are you stopping here?
Sorry, yeah, I'm stopping here. I'm sorry about it.
No, it's okay. Thanks so much, Tomoyuki, for this nice talk. Now I'm going to unmute everyone, and please accept that and give a big hand to our speaker. Now we're going to take questions. If you can either raise your yes. Are there questions? Please use the raise hand option. Yeah, so there is a question from, yes, okay, I see there's a question from Edward Witten, so I'm going to unmute. Yes, okay, Edward, you can.
Okay,
yes.
well, actually, I have a question that should have been right at the beginning, as you'll see. You said that for an integrable affine Lie algebra, the associated variety is trivial. So that should, but it's obtained by taking the quotient of the whole vertex algebra by what you called C2. So the current generator should be in C2, which seems to say that C2 is a descendant, sorry, that the generators are descendants. So I was puzzled, obviously I misunderstood that. So I can't tell if people heard my comments.
Yeah, I can hear you.
I think
you have, Tomoyuki, you have to unmute, yeah, you're muted.
Sorry. Yeah, so the associative variety is a trivial as a reduced scheme, but as a scheme, it's not trivial. So it's a fact point.
Okay, fine. All right. So what the statement means is that a sufficiently high power.
Yes, it's yeah.
Okay, thank you.
There is another question from David Agato. So the question is, how does the associative variety behave under VOA extension?
If the extension is finite, we expect that the associative variety is rationally equivalent. But if it's an infinite extension, we don't know. We don't know how to control. Does this answer?
David, does this answer your question? Okay, he's happy. He said thank you. Are there any further questions?
There's a question from Cameron Gosser.
Yes. Cameron, you can ask the question now.
Yes, very nice talk. I have a question. How much does this perspective from the vertex operator algebra help us perhaps in classifying the n equal to 2 theories or subclassifying them depending on some conditions? Is there a way to get insight into the totality of them in some form?
So if you believe this map is injective. This means that if you are able to classify the image, you should be able to classify the energy quotient.
But let's assume it's injective, but is there a way, I mean, this is probably a vast class. Is there a way like you classify it according to some sub-classification in terms of some complexity or something? Is there some kind of program there?
No, unfortunately, it's a big open question.
Okay, thank you.
Thank you. Are there any other questions? Yeah, Edward Whedon has another question. I unmuted you.
Yeah, as well as Higgs and Coulomb branches, there are mixed Higgs-Coulomb branches in general for n equals 2 theories. I assume what you've been calling the Higgs branch is the case where the Coulomb branch is trivial. But I wonder if mixed branches mean anything.
Sorry, I cannot answer that.
Okay.
Maybe someone else can answer for me.
I guess we can move on to the next question. I do not see any other question. So if there are no further questions, let's thank the speaker once again, and would move on to the next. We have about 10 minutes, so we'll take a short break, and we'll be back at 3 p.m. local time. Thank you.
Thank you for listening.